Okay, so we've talked about two acid-base theories in the last video. So again, there's the Arrhenius theory, where Arrhenius said an acid would dissociate H plus in water, and a base will dissociate hydroxide in water. And then there's also the Bronsted-Lowry theory, which said that an acid is going to be a proton or an H plus donor, and a base will be a proton acceptor. Okay, now there's actually a third theory, which is called the Lewis acid-base theory. This was devised by the American chemist G.N. Lewis, who's the same guy around that came up with the idea of the Lewis structures that we talked about in Gen Chem 1. So why do we need another acid-base theory? Well, there are compounds that act like acids and bases, but they don't have hydrogens to give up or accept. So there are compounds that act as acids or bases, but can't accept or donate hydrogen ions. So Lewis came up with this theory based on electrons. So he defined a Lewis acid as an electron pair acceptor and a Lewis base as an electron pair donor. Okay, in other words, and this is going to kind of set the stage for what you'll see in organic chemistry, a Lewis acid, this is the molecule that's being attacked. And in a Lewis base, this molecule is attacking. Is the attacker. Okay, so we can actually show a Lewis acid-base reaction between BF3 and NH3 by using electron dots. So let me draw some structures here. So here's the structure for ammonia, NH3, and I'm going to draw the lone pair. And then here's the structure for BF3. Okay, and I'm going to draw the lone pairs for the fluorines. Okay. And then boron has 6 electrons, it's happy. So the way this works, using a lone pair of electrons on the nitrogen, we come in and attack the boron. So according to our definition, the NH3 is, since it's doing the attacking, it's using the lone pair to do the attacking, this is a Lewis acid, a Lewis base. And the BF3, since it's being attacked, this is the Lewis acid. And so when these two molecules react, you form something like this, where the nitrogen is still bonded to the 3 hydrogens, but it's also got to bond to this boron that's also attached to these 3 fluorines. Which means that this nitrogen carries a positive charge because it's got 1 extra bond. The boron carries a negative charge because it's also got 1 extra bond. Okay. Now, before this reaction, the hybridization of boron and BF3 was actually sp2 because it was trigonoplanar, and the nitrogen in NH3, that was actually sp3. But here's the cool thing. While the nitrogen's hybridization didn't change, it still stayed sp3, the boron went from being sp2 and having the shape of trigonoplanar to sp3. So during this reaction, the boron in the acid changed its hybridization. And so that's pretty cool on how this all works. Another type of reaction, what if we looked at water and carbon dioxide? So here's a water molecule, and here's carbon dioxide. So using a pair of electrons from the water, from the oxygen, that's going to come in and attack the carbon, and carbon is going to break one of its double bonds with another oxygen and give that pair of electrons to the oxygen. So you form a compound like this. You've got the carbon that's going to be double bonded to one oxygen. It's going to be single bonded to one oxygen. Okay, and then it's also going to be attached to an oxygen, and that oxygen is also connected to the two hydrogens. And that oxygen has a positive charge. The oxygen that was connected to the carbon dioxide has a negative charge. So in this case, because water is doing the attacking, water is your Lewis base. And since carbon dioxide is a molecule that's being attacked, this is your Lewis acid.